Okay, so this is 3, 5 alpha, and it is the derivatives of the trig functions. You're going to start with the derivative of the sine function. Okay, so there is an analytical derivation which has a hole in it on page 142. Except we should know this much. Let's follow this much of it. This right here, dy dx, this is the difference quotient. We're trying to find the derivative of the sine. So the sine of x gets replaced with the sine of x plus h. That's your dependent value when you're subtracting up. Your denominator is x plus h, take away x, which they didn't write, which they should have written on this line, just gives you the h. From the first line to the second line, you have to remember the sine of alpha plus beta. That's what this is from pre-calc. Now, if you're not sure about how to do the sine of alpha plus beta, there is a PowerPoint specific to that in the Chapter 1 folder of Canvas. And if you need to go to that PowerPoint at your own pace, then I would strongly encourage you to do it. What happens is they come down here and they get to this point right here and say this thing equals 0. And how do they know? Graphical, the picture, or tabular, which means the table. That's why you're supposed to understand why that's 0, which is kind of baloney. Like, this is not, it's a graph or a table is not enough to do a derivation. So we're just going to do the same thing then. If they can do this, we can do a graph. So I go to y equals, and I just type in sine x. Because we will be able to do this when we get to chapter, well, to section 8.2, which we're going to do at the end of chapter 4. Here's the sine wave. And actually, I changed this color last period. I want to change it back. Sorry. So there's the sine wave. Okay. So if I go here, take a shortcut, and just graph the derivative, well, the derivative of the sine wave visually appears to be the cosine. You can see the blue graph just got shifted pi over 2 to the left. It's just a translation of the parent graph, the sine wave. And they tell us here in the tan box, the derivative of the sine equals the cosine. And if we went over here and we said, let's change this to cosine. And the blue graph becomes the cosine wave. Here comes the derivative. This looks like the cosine wave moved pi over 2 to the left, which is also the sine wave reflected over the x-axis. See, it's opening down through the origin instead of opening up. So that's going to give us this. These two derivatives. The derivative with respect to x of sine x is cosine x. The derivative of cosine is negative sine. The other 4 we can do with the quotient rule now. We can differentiate tangent by saying the derivative of sine divided by cosine. And the way we have this array set up, the reciprocal is across from the pre-image. So we'd say the derivative of cosecant would be equal to the derivative 1 divided by sine. We would do that by the cosine, by the quotient rule. Okay? But when we do L'Hopital, we'll be able to confirm that this is correct, but we're not there yet. Okay? So example 1, A is the product rule and B is the quotient rule. So we come back here. Here's example 1, which is on page 143 of your book, and it says, find the derivative of x squared sine x. Okay, so right away, you think back to section 3.3, and when you did the product rule with polynomials, you had an option. You could expand the polynomials and then differentiate with the power rule without using the product rule. But here you need to use the product rule. So how do we do it? First term, x squared times the derivative of the second factor. Derivative sine is cosine. Plus the derivative of the first term, 2x, times the second term, sine x. This is your expansion. This is your derivative. What does that mean? It means if I have x squared sine x, I go to y equals, and I type x squared sine x, that's going to be the blue graph. The orange graph is what we're going to get when we do the product rule. And does this make sense to you? Look what's happening here. The blue graph, starting at just to the left of -2, is going up just to the right of +2. In that window, the orange graph is above the x-axis because the blue graph is increasing. All right, that's logical. So I go back here. That orange graph is the graph of x squared cosine x plus 2x sine x. Well, that's not something you're going to guess. This is a non-calculator problem. But we could confirm it if we put this in y2 and turned off y1, then this would correspond to the orange wave that's is on our screen. And for B, you have cosine x. Now, what is it? It's u equals that. Well, don't worry about that. It doesn't matter what letter they use for the dependent variable. Cosine x divided by 1, take away sine x. So here's the quotient rule. I take the derivative of the parent, the denominator of the parent graph and square it. It gets pasted in the denominator of the derivative. I take the same term, paste it in the numerator, times the derivative of the preimage, derivative cosine. Subtract, that's why order matters, that numerator, cosine, times the derivative of the denominator. So from this line to this line, derivative of cosine is negative sine. Subtract cosine x, and they showed you here that 1, this is a sum, 1 differentiates to 0. Sine differentiates to cosine, but it was subtract sine, so subtract cosine. Now what? Distribute this over the parentheses. When you go to combine your like terms, you see the Pythagorean identity, sine squared plus cosine squared, so that's a 1. So you have negative sine x plus 1, commutative property of addition, which they wrote it this way, which is the same term in the denominator. So they reduced the numerator with one of these factors in the denominator, and they got this, which means what? If this is your graph, the u, then the instantaneous change is represented by this. Okay? So you're going to get practice with the quotient rule today on AP Classroom. So we're just going to worry about the problem 5, which is the product rule. Guys, you're going to use this as your model, part A, to do example 1A to do problem 5. We're not going to worry about problem 9. I have 4 subtract this product. So the derivative of the sum is the sum of the derivatives. Derivative of the constant 0, subtract first term times the second term, plus the derivative of the first term times the second term. And this is commutative property of addition. If you have this backwards, it doesn't matter. It matters in the quotient rule because you have a subtraction in the numerator. It doesn't matter in the product rule, the order of these terms. So you distribute the -1, and this is what you get, which means what? If this is the parent graph, the instantaneous slope is determined by this function. Okay? Now this, I told you, 3.5 is not on your quiz, but we're going back to parametric motion, which is on the quiz. So see if this helps you. So you have this weight hanging from a spring. Here's the picture. And here's what this weight is doing. It's going back and forth from 5 to -5, 5 to -5. Down here, the position is the blue graph. The derivative is the red graph. Well, the derivative would be the velocity graph. These two complement each other. That's your job, is to make a connection between the two modes. So I go over here and I say, let's see what this picture looks like. So I'm just going to have this travel along the line, x equals 1. It's going to go up and down. And I'm going to put the values, the height be the dependent values. We're keeping the x constant. It's going to travel vertically in the line x equals 1, and it's 5 cosine t. Now what? Well, we need to go to the window, because my y min and the amplitude is 5. My y min and y max only go from -4.1 to 4.1. So I'm just going to make these -6 and 6. I got the bouncing ball with the tail. I'm going to turn it on. I'm going to stop it, right? What happened? It started up here. Why did it start there? Because it's the cosine, and the cosine of 0 is 1. And the amplitude, the scale change, the amplitude was 5, so it started at 5, a height of 5. It's going down to -5. This is the picture in your book. We're just bouncing back and forth between 5 and -5. The velocity would be -5 times sine t. Are we getting that? Derivative of the cosine is negative sine. The acceleration is the derivative of velocity. Derivative of sine is cosine. So it tells you. What about position? The weight moves down and up between -5 and 5. Let me ask you some questions about the velocity and the acceleration, okay? So we're going to leave this up here, and you're going to go to problem number 11. Okay, so back to the picture. This is what's happening for that problem, number 11. It begins on the x-axis, goes up, and comes down. The weight begins at 0. Put 0 in the sine function, you get a 0. The height it reaches is 5. Well, at time pi over 2, the sine would be 1. 5 times that, it gets up to 5. At 3 pi over 2, 5 times negative 1 goes to negative 5. The velocity is 5 cosine t. The speed, the absolute value of velocity, is maximized at pi. Pi, 2 pi, 3 pi, 4 pi. And the speed is 0. Put an odd number times pi over 2. The acceleration is the derivative of velocity. That's maximized when the speed is 0. When the speed is 0. I'm sorry, the acceleration is 0 at n pi. Now, if you've had physics, you're well aware of this. If you haven't, and you're not taking physics this year, let's just make sure we understand each other. The SIGN of the acceleration does not tell us whether it is the particle's accelerating or decelerating. It's the agreement of the SIGN with the velocity. If they have the same SIGN, then this thing's accelerating. If they have different SIGNs, then it's decelerating. Okay? And example 3 just says the third derivative has a name, that's jerk. I mean, you just keep differentiating. Jerk is not an AP topic. It's in the book. It has to do with motion sickness, but that's not important to us right now. Okay? So that's that for 3, 5,